Welcome back to the class Computational Neuroscience, Neuronal Dynamics of Cognition. We have looked at attractor networks, and so far we have been considering only the deterministic Hopfield model. The deterministic Hopfield model means that the output of a neuron is just the sign function of its input. But neurons may be noisy. So what would that mean? What would that imply for the attractor dynamics? So as before, we have our interactions. We have stored random patterns, prototypes P1, P2, P3, maybe a total of M prototypes. And these prototypes are represented in the interaction matrix Wij. And as before, I sum over all the inputs. I sum over all neurons, j equal 1 over n. I take these prototypes in the form of the interaction matrix. I take the sum with the momentary state Sj, where Sj is plus minus 1 as before, and this gives the total input. But now the difference is it's no longer just a deterministic sign function. Now we have a probability that the next state is plus 1, which depends on this total input, and the total input is this. So what could this function look like? Well, for example, we could take a function where I plot here the input, and then say if the input is 0, I'm at 0.5, and if the input is big, I will somehow approach 1. There's no need that this is very symmetric, so it could also be asymmetric like this, a little wiggle. This is just a function g of h. And so the probability, if I have a strong input, that the next output is plus 1, will be very close to 1 if I have a big input. If I have a slightly positive input, it may, for example, be only 0.6. So the probability increases as we increase the total input, and it decreases if we go to negative inputs. So this is one of the examples. For example, you could take a hyperbolic tangent function with a slope factor 2. Factor 2 is the slope at this location. If you generalize and say I have here hyperbolic tangent of beta h, and I take beta equal 10 or 20, then it will become steeper and steeper. And if I take beta to infinity, then it really goes back to a step function. And this is the situation that would correspond to the deterministic model. So the total input is this h. This is this axis here. That's my total input. The total input is the sum over all the neurons. But since the weights are the same as before, since the state of the neuron is still plus minus 1, I can still define my overlaps as before, and I still get the same equation as before. So the only thing that has changed is the output. So now, if we look at this, so this is the total input, sum over all neurons, rewritten as a sum over overlaps. Now assume that there's only overlap with pattern number 17. What does that mean? Well, it means that the overlap with all other patterns is 0, and therefore, in this case, I would have g of sum over mu goes. I only have pattern 17, so it's pi 17 m17 of t. So now you see that there are only two possibilities. pi 17, what's this? This is the value of the pixel I in pattern number 17. So pi 17 is plus minus 1. It's black pixels or white pixels. Now think of all these different neurons. I have many neurons I which have pi mu equal plus 1. For this specific pattern, mu equals 17. Note that I wrote pi mu, but I really mean pi 17. So let's correct this. And I say for mu equal 17 for this specific pattern. Now for all these neurons with pi 17 equal plus 1, the probability that Si in the next time step is plus 1, given this input, is just g of, well, this is plus 1, so plus m17 of t. And then I have other neurons. I have many neurons I, where pi mu is -1. And for all these other neurons, the probability that the next state is +1 given their input, but it's a different input. The input of these neurons, they will have by this condition here, they will have a pi 17 -1. So I have g of -1 times m17 of t. So this is the probability that a neuron, which is supposed to be off -1 in pattern number 17, will actually be active, will have an output Si equal +1. Now what's the probability that one of these neurons, say in the same group, are not +1 but are -1, Si of t +1 equals -1, for the same input, this same group of neurons? Well, this is 1 minus the probability to be active. So it's 1 minus g of minus m17 of t. And the same argument could be made for the other group. Neurons that should be active, they have a +1 in this pattern, in our pattern number 17, can happen to be inactive. And their probability would again be 1 minus g. 1 minus the probability to be active is the probability to be inactive, to be at -1. So we have these two groups of neurons, and when I write here pi mu, I mean it for mu equals 17. This is my current pattern. I've assumed that there's only overlap with pattern 17, no overlap with other patterns. So for those two groups of neurons, we have a driving force of plus m17 if they belong to these plus pixels, +1 pixels in pattern 17. This is for pi 17 equal +1, and this is for pi 17 equal -1. Now let's work on this a little bit further. I see that on the right hand side I have the overlap at time t with pattern number 17. On the left hand side I have the state in the next time step. And I have two different groups of neurons, those that should be on and those that should be off. Should be off because the target pixel in pattern 17 is -1. Now the idea is that I would like to take this information, plug it in here, time step t plus 1, and calculate the overlap in the next time step. So let's do this. We are interested in the overlap in the next time step. We assume that the initial overlap with this pattern number 17 is non-negligible, is for example 0.4, and we want to find the equation for the overlap at the next time step. Now I want that there's only overlap with pattern number 17 and the overlap with other patterns stays 0 all the time. So I can really focus on pattern number 17. So now, given what we have seen on the previous slide, there are in fact 4 groups. There are those neurons that should be active, that means pi 17 equal +1, and happen to be active in the next time step. But there are also those that should be active and happen to be off in the next time step. Then there are those that should be off, which means pi 17 equal -1, but happen to be active in the next time step. And then there are those that should be off and actually are off. So let's put this together. So in my sum over all different neurons, I have the two groups of neurons. I have those which have pi 17 equal +1, and then I have those that have pi 17 equal -1. So for all those that have pi 17 equal +1, I will have in this sum a +1, and then I will have the state, but the state is Sj. Now Sj is also plus or minus 1. So Sj can be +1, and it will be +1 with a probability of being +1, which we calculated on the previous slide. So this probability of being +1 given that the pixel is +1 is just g of plus m17. Okay? G of plus m17. And then we have the second subgroup. It's still pixel +1, but now it could be, so this is the pixel value, but now it could be that the neuron is actually inactive. So it could be that the neuron, despite the fact that it should be on, is off. So I have a -1, and what's the probability for this? Well, it's 1 minus the probability that is on. So it's 1 minus g of plus m17. So all this was the first group. Now let's work on the second group. Put it here. I have a plus, additional contributions. It could be that this pixel is negative. That's a -1. And then it could be that this neuron is currently active. It has a value of +1. And what's the probability for this? It's g of minus m17. And then I have the neuron should be off. pj17 is negative. I have the situation that the neuron actually is off, and it is so with probability 1 minus g of minus m17. Okay, these are the 4 different cases. Plus plus, plus minus, minus plus, minus minus. Now, how many neurons do we have in each of these 4 subgroups? Well, we can suppose that we have stored random patterns. So suppose that exactly 50% of the pixels are on, are black, or +1. So I would have 1/2 n of all these possibilities. And then the remaining is 1/2 n for all the other possibilities. But then I have an additional factor 1/n in front, which will just cancel the n. So let's sum this up. I have plus g of m17. I have minus 1 minus g of m17 with a factor 1/2, since the n goes. The n also goes here, plus 1/2. I have a -1, g of minus m17, -1, plus 1 minus g of minus m17. Let's collect the terms. I have g of m17, let's put the brackets in here, that's what I meant, minus 1 minus g of m17. This gives 1/2 2g of m17 minus 1 plus 1/2 minus 2g of minus m17 minus 1. So I have 1/2 times 2, which makes g of m17. Then this 1/2 gives a minus 1/2. And I made a mistake here. Okay, this is a +1 that comes in here. So I have minus 1/2 plus 1/2, they go. I have 1/2 minus 2 gives minus 1, g of minus m17. So this is the overlap m17 at time t. And on the left-hand side, I have the overlap at time t plus 1. And the combination of these two g's I will just define as a function f tilde. So I take the overlap at time t, I pass it through this function f tilde, I get the overlap at time t plus 1. So let me summarize this. The result of the calculation is that I have some function which I call f tilde. I take the overlap at time t, pass it through this f tilde, and get the overlap at time t plus 1. And of course, pattern number 17 is completely arbitrary. It could be any pattern, so let's call it pattern nu. The state of pattern nu at time t plus delta t, or t plus 1, the state in the previous time step. So we go from t to t plus delta t. And suppose we have an initial overlap of some value, some small value, maybe 0.4 or 0.6. Then we just read off the overlap in the next time step. And this would be the overlap in the next time step. Okay? But then this is the overlap in time step t plus delta t, which we will re-inject. So we will re-inject it here. Now if you think about it, to find this re-injection point, you can just go to the diagonal, and this would be the re-injection point. Okay, and then we go up here, and this would be the overlap in the next state. We re-inject, we are here, overlap in the next state, and so forth, and you see it will converge to this fixed point, and this fixed point is stable under this dynamics. If I start with a bigger overlap, I would go downwards. So this is a stable fixed point. So what I've shown is that if you start in a certain pattern, for example, a pattern number 3, which has an initial overlap of 0.4, then you may take a couple of steps, and then I arrive at the fixed point. The fixed point sits very close to the perfect pattern. It doesn't sit at overlap 1, for example, at 0.97, or it may sit for pattern 17. The fixed point may sit at 0.91. The important fact here is we converge to a fixed point where the pattern is nearly perfectly retrieved. If I start over here, it will converge to some other prototype, maybe pattern number 12. If I start over there, it will yet converge to a different prototype. So depending on the initial condition, I will move towards the fixed point. The network is attracted towards the fixed point, and that's why it's called the attractor memory. Now you note that this is true here in the setting of the stochastic Hopfield model. So what have we seen? Memory retrieval is possible just with stochastic dynamics. We don't need the deterministic dynamics of the Hopfield model. If we converge to the fixed point will be very close to the pattern, but it will not have a perfect overlap of 1, but a large overlap. For example, 0.95 or 0.97. Now, for the calculations I did in this section, I sort of assumed that if I have a large overlap with one pattern, I can keep the other patterns at 0 overlap. Now, this is implicitly the assumption of orthogonal patterns. Now, note that random patterns are nearly orthogonal. Therefore, the argument should also work for random patterns. So we have generalized the Hopfield model to the setting of stochastic dynamics, and we have shown that the concept of attractor dynamics is much more general than the original Hopfield model. Now, to wrap this up, have a look at the quiz and see you for the next section.